So welcome back. We've arrived at another very interesting video, in this video I'm going to talk about the dynamics of a spinning rocket. So these last videos should make you think a lot about how to design the airframe, and when it's when I talk about designing the airframe and stability, it's more about how to design the fins, how to design the if you should give it roll, if you shouldn't, how much. So these are probably the most important videos on this section. So a spinning rocket. Well, the dynamics of a spinning rocket are pretty complex. So first of all, what I'm gonna do is define properly the axis that we're gonna use for the rocket. So I'm getting better at this. So what Mandel uses in his book on topics in advanced model rocketry, what he does is he uses this axis, Z axis here, and this is center of gravity, and then Y axis here, and shooting tube X axis. I'll put it here, and the Z axis doesn't follow the rocket roll. So what this means is that if the rocket rolls, well, the Y and X axis are fixed. You can think of X and Y as axes that are like always in this plane. Okay, they're gonna, while the rocket is shooting up, well, X and Y are always gonna be in this plane. So and Z. So if the rocket slightly tilts and do this again. If the rocket slightly tilts, this would be tilting in the X-axis, while we have an angle of attack in the X-axis. Okay, so and on the I'd call the X-axis, I don't know, pitch, and Y yaw, but we don't differentiate it because it's symmetrical. So I'll treat they're different angles, but after all, they sum up to give the rocket a tilt from the vertical. All right. So if we have a rocket that is spinning, the dynamic response, the transient response to a perturbation. So imagine this is spinning at a roll rate omega z. If we give this a kick, if it weren't spinning, we'd only have an alpha x, right? We wouldn't have the rocket tilting in we wouldn't have angular movement in the y-axis, right? But if the rocket is spinning, we say that the equations are coupled. So we do have we do gain an angle of attack, an alpha y and an alpha x, if we just give a kick on the y-axis. So what this means is that we're not longer going to talk about just one alpha, which could be alpha x or alpha y, any kind of angle of attack. We're going to have to talk about the two angles. So the response, the general response to a rolling rocket is going to look like this. Let me see. It's going to be the sum of two damped sinusoids. So this means we have one damped sinusoid here, sine, which has its own angular frequency and its phase angle. We're not going to care much about the phase angle, just get the general idea. And then a second sinusoid, which has another amplitude, another inverse times constant. This isn't sine, sorry, because there's a phase angle of 90 degrees between two axes. This is going to be, no, sorry, this is actually sine. I was right. 1 second. Let me finish this and then think. All right. And then on the y, the alpha y is going to be the exact same damped sinusoid, but its phase angle is 90 degrees. So instead of sine, we have cosine. So yeah, it's the exact same damped sinusoid, but just dephased by 90 degrees. So that's why you have cosine here. So I'm going to discuss what these equations mean. We're going to visualize them in the next video. So yeah, it's quite different from a non-spinning rocket. And I can tell you now that this is we have a slow mode and a fast mode. This means that this damped sinusoid is gonna dampen out pretty quickly compared to this one, probably quicker than a damped sinusoid we would have in a non-rocket rocket, and also the amplitude is going to be lower. All right, so we have like a slow mode that is gonna like define our movement. Okay, and then on top we're gonna have like on top of that slow mode, which is going to define the movement, we have like perturbation. We can see this is like a perturbation term. Okay. So the thing is, the big difference between a rolling rocket and a non-rolling rocket is that our inverse time constant, let's put it spin, can be extremely large if we spin this up, if we spin the rocket a lot. Okay. What does it mean that? How is it going to affect the dynamics of a rocket? Well, if we have t here, let's just plot alpha x. If we had a non-spinning rocket, if it found a perturbation, maybe a step input, it would respond like this. But if we have a d that is so low, did I say high before? By the way, higher d, higher inverse time constant means a faster restoration. So if we have a low d, we're gonna have a really low restoration. This seems like bad because don't we want like the rocket to restore really quickly from a perturbation? Well, if it's so low, this inverse time constant, if it finds a step input, well, it's going to take so long to gain an angle of attack. It can look like it's actually even it can look like the perturbation isn't actually affecting it, and maybe at this point the perturbation is away, so it goes back down to alpha x0. So this is why, for example, unstable projectiles are spun up. If you spin a bullet super fast, well, a bullet, as we saw before, is unstable. It has a negative, it has a positive cm alpha. This means at a small angle of attack, it's going to try to unstabilize even more. But if this is rolling, I don't know at which frequency bullets roll. I don't care, but I guess it has to be pretty fast, because again, this is an unstable projectile. If this is spinning super fast, then if it finds a certain angle of attack, it's gonna be super stable, and it's gonna take ages to feel that perturbation, and maybe then again in a bit of time perturbation is gonna be out. So that's the idea behind roll stabilization. Okay. And there are other perks about roll stabilization, as I'm gonna discuss in a moment. Let's see. Maybe we can talk about the steady response to sinusoidal inputs. So the cool thing about roll stabilization as well is that, imagine that we have a small, let's put it here, a small thrust misalignment. If this is the roll axis, imagine that our thrust force is slightly misaligned. Okay, so we have this force that is gonna create a torque on the axis. So if we try to imagine it, if we imagine that this thrust force is always in this direction, this means that when the rocket spins a bit, well, this moment is gonna change. It's gonna move around the rocket. Okay, but remember that y and x were constant. So what we're gonna have is what the x and y axis are gonna feel is a sinusoidal moment, not because the rocket is spinning. So, and we could conclude the same if the rocket had some misalignment with the fins that caused a certain constant moment. So any imperfections are gonna turn into a sinusoidal force. This happens when the rocket is spinning, of course. If we had just a constant, say a wind shear, well, it would be only on the y-axis. This wouldn't be a sinusoidal input. But any imperfections that there are going to be always in the rocket are going to turn into a sinusoidal input of this style. Let's put and the frequency is, well, the angular velocity of the sinusoidal input, of course, is going to be the roll rate. And yeah, if you want to add a phase angle. And on the y-axis, it's going to be exactly the same, but just dephased from 90 degrees. Therefore, it's going to be a cosine. Okay? So we get the idea that on the two axes, it's going to be the same function, just dephased from 90 degrees. So we might as well do the study just for one of the two angles, and we're going to get the same same steady response. Not quite the same. You can check Mandel, but with all the simplifications we made, we can conclude that it's going to have the same natural frequency and the same damping ratio and the same gain. How do I call gain? I think I just call it K. It's going to be practically the same. All right, maybe the gain is going to change a bit more, but the most important things, which are these two, these are going to influence. Remember the resonance. They're going to be the same, and that's why I didn't talk about the resonant natural frequency and the resonant damping ratio. I just didn't make a difference between the two. So what I told you in the previous video about resonance and the natural frequency still holds. All right. So that's interesting. So what else? Yeah. So what I mean is that remember that any small asymmetries caused by the rocket or the aerodynamics, the airframe, are always gonna cause a sinusoidal forcing on a rolling rocket. That's why you always have to worry about the steady response to sinusoidal forcing, because you're always going to have it if the rocket is spinning, and the rocket is going to spin, want it or not, probably due to small imperfections. So that's why we always want to worry about resonance, because this moment can be super small. This perturbating moment can be super small, but because the rocket is such an undamped system that even the smallest, the tiniest perturbing moment, if it spins at the natural frequency of the pitching or your response, it's going to blow up. Okay. All right. Let's see if I wanted to tell you something more. Let me think. Oh yeah, and the cool thing about spinning at above the natural frequency, above the danger zone, which is the case of Rexus. So if we're spinning at here, at this frequency, which is way above the natural frequency, which is the case for NASA rockets and Rexus rockets. Well, here the gain is negative, so any kind of imperfections we have in our construction, thrust or any misalignments on the fins or whatever, which causes a sinusoidal forcing, well, it's going to be negligible here, because we have negative gain. So if we have this input, the rocket is barely going to feel it. So that's a nice thing of rolling rocket as well. And okay, so it really looks like roll stabilization is awesome for various reasons. First of all, if a rocket finds a perturbation, it's going to very slowly diverge from its path, very slowly, and slower if we spin the rocket higher. Oh, I didn't talk about these values. All right, I might as well write them down. You can find them in Mandel, but I'm just going to write them down. I'm not going to show you the derivation. I did it once, and trust me, I never ever want to do it again. Thank you, Mandel, for doing this. Yeah, trust me, and you don't want me to do it either, because I'd give you another 1 hour videos. So okay, here it is. The inverse time constant for the fast mode. looks like this. Remember what C2 is with R values. I think it's if I recall correctly, C2 is this, and C1 we define it as phi prime QA. Manual uses C2 and C1. I prefer to use, these variables. Okay. C2, and then we have this over here. Doesn't look too bad, doesn't it? Well, wait a moment. I'll just, you know what? I'm just gonna call it to make it more compact, D1 or D2. So you have the two equations here. Cool. And then what is this angular velocity? Well, this angular velocity is when the fun comes. Okay. This is the roll moment of inertia for the rocket. Okay, when I don't put a subscript, remember it's a longitudinal moment of inertia. Now we have to talk about both of them. Okay, I'll put a plus. And then uses this F, strange F. Okay. I'll just pause the video. Alright, doesn't look so innocent now, doesn't it? And by the way, for the second moment, the difference is only with this. If I'm not wrong. Yeah, that's the difference between the two moments. Alright, and now I'm leaving. So you can do a check. You can put like some numbers here. I'm not going to do it for you, but you can put, for example, Rexus C1, C2. You can guess the moments of inertia. You can put 4 Hertz roll rate, and you can check this. This inverse time constant. You're gonna see. I'm not sure how much it's gonna differ, but I can guess it's quite a lot. And for, am I leaving something else? Yeah, I'm leaving the amplitude. I'm not going to talk about the phase angle. The phase angle, well, it's kind of. Let me check the amplitude. 1 second. For you. You know what, the amplitude, I'm not going to write it down because here comes all the eternal equations. So it isn't so relevant for the dynamics of a spinning rocket. I think the most relevant thing is knowing that the value of the inverse time constant. After all, gain and this is a secondary thing. Because the most important thing is knowing that it's going to take super long for it to find for it to die out. Okay, for the perturbations to die out. And I think I'm going to leave it here. The next video I'm going to talk about what the hell these equations look like. In reality, it looks it's pretty simple, but I'm gonna film a video because it's kind of hard to draw it. Right, see you in the next video.